Today, we're going to learn about a powerful new tool that we have at our disposal for calculating electric fields and electric flux. That tool is Gauss's law. So in learning about Gauss's law, we're going to review a little bit of electric flux. We're going to talk about positive, negative, and zero charge distributions inside a closed surface. And we're going to talk about a very important observation for us to make. And that observation is the symmetry of the charge configuration. Let's begin by saying that the net electric flux through a closed surface is positive when that surface encloses a net positive charge. Illustrate it when more field lines leave the closed surface than enter it. So if we've discussed in previous lectures, if we have a surface that is enclosing a volume of space, and we look at electric field lines that cross the surface going in, and electric field lines that cross the surface going out, based on the number of field lines crossing the surface in and out, we could determine whether or not the total charge inside that volume is positive or negative. So in this example, I have 1, 2, 3, 4, 5 field lines going out. So 5 out. We have 1, 2, 3, 4 field lines going in. So the net is 1 field line out. That positive coming out means that inside we have more positive charges in that closed surface than negative charges. Now, we also talked about what if we had a negative charge enclosed by a surface. So the net electric flux through a closed surface is negative when that surface encloses a net negative charge. Illustrate it when we have more field lines enter the closed surface than leave it. So let's say we just add a couple more field lines here. So we have another field line going in and another field line going in. So now we have 6 field lines going in and 5 field lines going out. What that means is we have a net of -1, or in other words, 1 field line going in. This signifies that we have a net negative charge that is enclosed inside this sphere. So depending on the number of field lines, depending on the electric flux through a closed surface, we could figure out whether we have a positive or a negative charge. And for one more situation is that we know that the net electric flux through a closed surface is 0 when that surface encloses 0 net charge. So if we just add one more field line going out from the surface, that additional field line means we have 6 field lines going out, 6 field lines going in. So the net field lines is 0, which means either we are enclosing 0 charge or 0 net charge. So what that means is we're going to have an equal amount of positive and negative charges enclosed by that volume. So since we know whether or not a volume of space encloses a positive charge, a net negative charge, or a net 0 charge based off of whether the electric flux across that surface enclosing a volume is positive, negative, or 0, there's a natural question that we should ask. Is there a way of determining how much charge is inside that volume of space? Well, before we answer that question, let's revisit our formula for electric flux. The electric flux through a surface of area dA, so this is our area differential. And actually, let's go ahead and draw this out for a sphere as we are talking. So this is a sphere of total area A, but if we look at a tiny surface area differential, dA, for that tiny spherical rectangle, we're going to get a tiny amount of electric flux passing through that surface. That electric flux is given by the surface integral of the electric field. So this is where we can say that the electric flux, that tiny bit of electric flux, d phi, through a tiny surface element, dA, due to an electric field, E, is equal to the component of the electric field that is parallel to the surface vector. In other words, that's where the dot product comes in. So let's use electric flux to see if we could figure out if there's a way that we could determine the amount of charge that's inside a certain surface. Which of the following spherical surface has the largest electric flux? I see that we have 3 spheres. The 2 spheres on the left have different radii and they're centered on a positive charge. The sphere on the right encloses equal amount of positive and negative charges. From the diagram, I could say that the sphere on the right has 0 electric flux. So I will call that right sphere. I'll just say R sphere. The flux for that sphere on the right is 0. We could also say that the flux for the sphere on the left is going to be a positive value. Now, if we look at the sphere in the middle has 6 field lines crossing the surface. So the sphere in the middle also has a positive flux. And we know that flux is proportional to the electric field and the surface area. Well, let's see if we could go ahead and do this calculation. And let's compare the electric flux for the sphere on the left and for the sphere in the middle. And let's acknowledge that both spheres completely enclose a volume of space. That means the sphere is the boundary between the region outside of the sphere and a region inside the sphere. Let's start off for the sphere on the left. So in drawing the sphere on the left, this sphere on the left we'll say has an arbitrary radius r. And let's illustrate the electric field. The electric field is spherically symmetric, matching the fact that point charges have spherically symmetric electric fields, and the sphere that the electric field passes through is a sphere, so that's nice. Well, let's see if we could calculate the electric flux for this. And to do this, we're going to need to know the relationship of the electric field to a surface differential. Now, that surface differential, we could just take an arbitrary spherical rectangle. This is my spherical rectangle I'm going to take, and look at the surface area differential for that spherical rectangle, dA. And we need to look at the relationship between that differential of area and our electric field. Notice that the angle between those two, which I'm going to signify that as theta EA for the angle between the electric field and the area differential, notice the angle is 0 degrees. Another thing that I want you to notice is that the symmetry of the electric field matches the symmetry of the sphere. And what that means is the electric field lines at any point on the surface of the field, on the surface of the sphere, look like the electric field lines at any other point on the surface of the sphere. The electric field is perpendicular at all points on the sphere, and the electric field has the same magnitude. So relative to different surface differentials, we could say that the electric field is constant relative to a tiny surface element. Well, let's use this fact in calculating our integral. We have the integral over this closed surface of the electric field and area element. Let's go ahead and move this a little bit so we could have more space to write. So here we have the electric flux across that sphere. Now let's go ahead and rewrite this integral using an alternative form of the dot product, which is the magnitude of the electric field times the cosine of the angle between the electric field and an area element times our area element. Now we said that the theta is 0 degrees, which means that cosine of 0 is equal to 1. We also said that the electric field is constant relative to any surface element on the surface of our sphere. So we could pull the electric field magnitude outside of the integral, and that leaves us with just an integration involving the surface area A, which ends up being the product of the magnitude of the electric field and the area of the entire sphere. Okay, so let's look at that. Magnitude, so we have the electric flux for that sphere on the left is equal to the magnitude of the electric field times the area of the sphere on the left. And you know what? If we were to do the exact same work, we would get an equivalent expression for the electric flux for the sphere on the right. That would also be the electric field at the surface of the sphere, which I'll indicate with a subscript R for the electric field at the surface of the sphere, not on the right, rather. I should have said on the middle. So I'll use the variable m to indicate the electric field at the surface of the middle sphere, and m for the area of the middle sphere, and I'll use L to signify the electric field at the surface of the sphere on the left. So we could compare these two expressions. Let's look at the flux for the left. Well, in order to find the flux for the left, we need to know what the electric field is due to a point charge. Now, Coulomb's law told us that, and when we worked Coulomb's law with the definition of the electric field being force per unit charge, we got an expression for the electric field due to a point charge is equal to KQ over R squared for the electric field magnitude due to a point charge, where R is the distance from that point charge. Well, that means the electric flux for the surface on the left is given by the electric field, which is K, Q. I'll call this R L squared. And now we need an expression for the area. Now remember, area of a sphere is given by 4 pi r squared. So we could put in the area then is 4 pi rl for the radius of the left sphere squared. Again, this is the electric field, and this is the area. Oh, look at this. We have a radius squared in the denominator, a radius squared in the numerator. Okay, so let's take a look at this. I'm going to just erase this for now. So when we take a look at this, we get the electric flux is equal to kq times 4 pi. Well, you know what? I know that Coulomb's constant K can be written as 1 over 4 pi epsilon naught, and we have a Q and a 4 pi left over. But notice the 4 pi in the numerator cancels with the 4 pi in the denominator. So the electric flux through the smaller sphere on the left is just simply Q over epsilon naught, where Q is the amount of charge that is inside our sphere. Okay, so now we have an expression for the electric flux on the left sphere. Now let's get an expression for the electric flux on the middle sphere. The electric flux on the middle sphere is going to be K, same Q, over the radius of the middle sphere squared. Now, this quantity just comes from the magnitude of the electric field on the middle sphere. Now, the surface area of the middle sphere is 4 pi r sub m quantity squared. And the next line, well, notice we have a radius of the sphere squared in the numerator and the denominator. They will cancel. So this becomes the electric flux of the middle sphere is equal to kq. Oh, look at this. kq times 4 pi. Oh my gosh. This is independent of the size of the sphere, because when we do the next couple of steps, the next couple of steps is exactly the same. 1 over 4 pi epsilon naught, q, 4 pi, the 4 pi's cancel. We get the exact same expression. The electric flux through the middle sphere, based off of how much charge is enclosed by that middle sphere, is equal to the electric flux on the smaller sphere. Wow. What this is saying is the flux through an enclosed surface, an enclosing surface, depends only on the amount of charge contained inside the surface. It doesn't depend on the size of the surface. It doesn't depend on the geometry of the surface. It doesn't depend on the strength of the electric field. This is saying the only thing that matters is how much charge is inside the sphere. This simple example leads us to a very important conclusion. It leads us to Gauss's law. Gauss's law gives us the connection between a closed surface and the amount of charge inside that surface. Gauss's law says that the total electric flux across a surface that completely encloses a volume of space, and that's what this circle through the integral means. That circle through this surface integral means we are a closed surface, that surface encloses a volume of space. The surface is a boundary between a volume outside the surface and a volume inside the surface. And Gauss's law says that the total electric flux through a closed surface is equal to the amount of charge enclosed by that surface over epsilon naught. This is such a powerful expression. In other words, the total electric flux through a closed surface is directly proportional to the amount of charge enclosed by that surface, where the constant of proportionality is 1 over epsilon naught, the permittivity of free space.